So we've seen 3 different attacks on WPA, and all of them come back to one core issue, I would say. And the core issue is that there's only one source of secrecy, and that's the Wi-Fi password. Every other source of secrecy, the key in blue, the key in purple, are all derived from the same source of secrecy, and it's the Wi-Fi password. And the Wi-Fi password is something that everybody on the network knows. So in other words, there's only one secret, and everyone has the same secret. So for example, the forward secrecy attack was made possible because in the future, someone might learn the Wi-Fi password, and that's the only secret that we're using, and it's shared across a bunch of people. So someone who learns that Wi-Fi password can then go and decrypt other people's messages, which is not great. And likewise here, the only secrecy is from the Wi-Fi password, and it's the same shared by everyone. So anybody can record one of these handshakes and use it to brute force the Wi-Fi password. So this is something we don't like. It's the fact that everyone has the same password that they're using, and that's the only source of secrecy. So the fix is to give everyone a different source of secrecy that's unique to them. So this is the difference between having a website where there's one single password that everybody uses to log in versus a website where everyone has their own unique username and password. Both are valid approaches, but in order to fix some of the problems we've seen, we're going to switch our model from a single password that everyone shares to everyone having a unique username and password. And this is the model that Berkeley's secure Wi-Fi network uses. Nowadays it's EduRoam. For those of you who are older, it was AirBears 2. For those of you who are ancient, it was like Telebears or something. But all of these are Wi-Fi networks that use an upgraded version of WPA. It's called WPA Enterprise. And the older version that we saw was called WPA PSK. So now you know what that stands for. So anyway, in this upgraded version of WPA, we're going to give everyone their own unique username and password. So whenever you register with this network, say you become a student at UC Berkeley and you sign on to EduRoam, EduRoam gives you a unique username and password only for you, and nobody else shares your password. And in the future, if you ever want to authenticate to the network, what you'll do is you'll walk up to some authentication server. And this is new, you haven't seen this before, but we'll go to some authentication server, which we're building as a new thing, and we'll form a secure channel to them using some tools that we'll see later, so nobody can tamper with this channel. And you'll send your username and your password to this authentication server. So basically, you're doing a login. This is a little bit different from what we've seen previously. You are logging in by typing in a username and a password. Now, if the username and the password are correct, then the authentication server presents you a randomly generated key in blue, and it also presents that same randomly generated key in blue to the access point, and now both of you have a random key in blue, and your handshake can proceed as normal. So in pictures, what we've basically done is we've deleted this first step where both of you derive the blue key from just the Wi-Fi password, and we've instead installed the new step where the client logs in to some third-party server, and if the login succeeds, the third-party server gives the client a unique key in blue and gives the access point a unique key in blue. This has the consequence of making every single handshake different. We're no longer deriving a PSK just from the Wi-Fi password. Everyone gets a different PSK for every handshake every time they log in with their username and their password. So why is this good? This solves some of the attacks we've talked about. The rogue AP attack is no longer possible, and the reason is because this authentication server has additional safeguards against people impersonating it. That's something we'll talk about when we talk about TLS later. But for now, you can imagine this server has some sort of certificate that says, this is who I am, and nobody can impersonate me. So this attack is no longer possible if we have a trustworthy third-party authentication server. What about the brute force attack, where we recorded a handshake and went into the cabin to try out a bunch of different passwords? That's no longer possible because there is no Wi-Fi password that's used in the derivation that we can guess. Instead, the derivation is based on a randomly generated PSK, and if you imagine this is some 256-bit random value, the probability of guessing a 256-bit random value is basically 0, so that's not going to happen in anyone's lifetimes. And forward secrecy can be achieved by discarding that PSK once you're done using it. So if we go back to one of these handshakes, if this PSK, instead of being derived from a password, is a one-time use value that is used in the handshake and then deleted forever, an attacker who records this entire handshake in the future will still not be able to decrypt messages because they will not know that key in blue. It's been discarded and thrown away. They will not be able to derive the key in purple. So if you use WPA Enterprise as we've described, you can solve the 3 attacks that we talked about by having the access point be authenticated, by using long random PSKs that are hard to brute force, and by discarding the PSK after each use to preserve forward secrecy. So this is WPA Enterprise and how it stops the attacks we've talked about. And all of this is in the context of WPA, the process where you connect to the network for the first time, and it doesn't solve other problems involved with ARP or DHCP spoofing. So this is specifically for the process of connecting to a wireless network.